talk will be by Thomas Hughes from McGill University, and he'll be talking about the compact support property and finite propagation speed for some SPDEs.
Yes, so thank you. Thank you very much, all of you, for coming this morning, and thanks to the organizers for the chance to give a talk here. So I'm going to talk about some stochastic PDE, and the first thing I'll do is write it down. And the equation I want to look at, we all know what we mean here, is we have a stochastic heat equation with just a noise term like this. And this we can think of as being a Gaussian space-time white noise, and we'll look at this for the time being in one spatial dimension, where we have solutions with no difficulty. I'm planning to give kind of a historically minded talk. I'm going to survey some properties of these things and some of the methods that have been used to study them. And at the end, maybe discuss a bit of my ongoing work in the area, but most of what I'm going to talk about is not very new. So hopefully it's new to some of you, otherwise I apologize. Now, just to kind of get situated, SPDE of this form, and gamma is going to be positive. And I want to talk about non-negative solutions. So SPDE of this form do not require as an elaborate solution theory as, for example, the one Marcus was just talking about. This is not in the singular KPZ kind of paradigm. So the solutions for SPDE of this form that I want to talk about have been constructed, a much longer time ago using the more classical Ito-Walsh solution theory. So we understand these as solutions to some stochastic integral equations. And so once you've defined the stochastic integral with respect to this martingale measure, the derivative of the Brownian sheet, we can basically define solutions to this and start talking about them. And so if we're not working very hard to construct solutions, then we should probably work hard to tell you about their properties. So what I'm going to talk about in particular is when a SPDE like this has compact support and when it does not. And so you can probably infer, if you're unfamiliar with this, that, well, sometimes the solution to this equation will have compact support and sometimes it will not. I have more of a branching background, so I'm kind of reaching here to make this relevant to interacting particle systems. But so here I'm just going to mostly talk about the stochastic heat equation or a heat equation now with a noise term. But if you then add an additional reaction term for some kind of nonlinear reaction like of FKP type, that's going to then be quite related to various interacting particle systems in a few ways. One is that if instead of taking a hydrodynamic limit of some interacting particle system, you take a different scaling so as to obtain a truly stochastic limiting object, then you'll often end up with an equation like this, but with an added reaction term. And the other relation is that oftentimes, if you're frustrated by studying your microscopic dynamics associated to an interacting particle system, you can just take the PDE and add a noise term and study that as a kind of phenomenological model for the same sort of dynamics. And I'll try to tie in IPSs a few more times as we go on. But so when does a solution to this have compact support? Well, if we get rid of the noise term, we have a heat equation. And the first thing you know about the heat equation is that supports propagate instantaneously. So the density is going to be positive at all times and all values of x. And so clearly the noise may have something to say about this, as we'll see. So I don't have, this is quite an old theorem, and it's proved over the course of several works, which are all about as old as I am. So I clearly had nothing to do with it. And that's if gamma is less than 1. So let's just say S of x of t, that'll be the closed, just topological support of the solution to this equation. This is compact. And if gamma is greater than or equal to 1, then we have the more familiar behavior coming from the deterministic dynamics, which is that this is positive. For all times and places, period. So let's move over here. And so now what I want to do is kind of give the history of this theorem, because it's proved over the course of 4 or 5 different works. And in doing so, emphasize some of the different techniques used to show this, and also kind of give interpretations for the meaning of solutions to such an equation. So the very quick historical lesson is that the first case you can prove, and we'll see why shortly, is gamma equal to a half. And so this is ISCO. And then gamma strictly less than a half is ISCO and Shiga. The full range gamma less than 1 is Perkins and Mueller. And the other case proves that you have the instantaneous propagation of support is Mueller. Now, I'm mostly going to focus on these first three cases and discuss the compact support case. This case is also interesting, but that's just not going to feature much today. And so, again, for a lot of us, we've seen equations like this. You've probably seen it for particular values. Most commonly, you'll see gamma equals 1, then you've got a linear multiplicative stochastic heat equation, or gamma's 0, then you've got an additive equation, and gamma equals a half, in which case we've got this branching type behavior, which I will now discuss. So the reason that the case gamma equals a half is special is because in that case, the solution to this equation is the density of a super Brownian motion in one dimension. And well, usually if I'm talking about super processes, I'll spend about 15 minutes making sure the audience is on board and knows what they are, but due to time constraints, you'll get the 15-second version today. The super Brownian motion is the measure valued limit of critical branching Brownian motion. It arises as a limit of a lot of different objects, but that's kind of the most intuitive one. So you're taking a high infinite particle limit for some branching particle system, start with order n particles, and you view the state as a measure by keeping track of the empirical measure. And to keep masses tight, you'll give each individual a mass of 1 over n. So you put a Dirac mass of 1 over n at the location of each individual. You've got this measure valued process, and you simultaneously accelerate the branching rate. So branches on, you're branching at rate n. And if you do this and you take the limit as a measure valued process, you get what is called a super Brownian motion. So you can think of it as an evolving mass distribution, which is comprised of a large number, in fact, infinitely many individuals, all of them contributing an infinitesimal mass. And they're all undergoing independent Brownian motion in space, but they're also all branching at an infinite rate. So there's a lot of n equals infinity in there, but for intuition, you just make n finite, and you've got this large measure valued branching process. And so, we all know what a picture of this kind of thing looks like. Maybe it'd be a bit more irregular. And so this is time going forward. And so the measure at time t is going to be comprised of kind of the contributions from all the individuals who actually survive until time t. That's what a super Brownian motion is. Now, so it's a measure valued process, but in one dimension it has a density, and the density solves this equation. So for ISCO to prove this result, that the solution to this equation of compact support when gamma is equal to a half is just a matter of showing that super Brownian motion has compact support. And this is a branching type process, so you have tons of tools at your disposal. In particular, there's this powerful duality theory via the Laplace transform, which plays roughly the same role that generating functions do in the classical theory of just regular branching processes. And so, ISCO proves this now without even touching the SPDE. I think it was only around the same time we learned that the density solved this SPDE. But nonetheless, using basically branching and super process methods, we get that for gamma equals a half, we have compact support there. Now, to see how it works for gamma not equal to a half, well, I'm going to give a kind of general idea in a moment. But you can take a more analytic approach, return to the equation, and well, what's going to happen? If we just had a heat equation, it's going to be positive everywhere. So clearly, it's going to get small, but the question is then, when is the noise powerful enough? When are the fluctuations caused by the noise powerful enough to actually send the solution down to hit 0? And so that just corresponds to how big the noise coefficient is when the density is small. And basically, the smaller gamma is, the more highly non-Lipschitz gamma is less than 1, then the more non-Lipschitz and relatively large to the size of the state this noise coefficient becomes as we get to small values. So it stands to reason that we'll have larger fluctuations caused by the noise, the smaller gamma is. So once you know that you have compact support for gamma equal to a half, it stands to reason that you should also have it for gamma less than a half. I don't know if that's exactly, you have to make that rigorous somehow, and they've managed to do it. and prove this result. Now, by the same token, if you go in the other direction, you make gamma bigger than a half, or the bigger you make gamma, the smaller the fluctuations of the caused by the noise will be when the density is small, and therefore they'll have a harder time driving the solution down to actually hit 0. So when gamma goes above a half, kind of all bets are off. But as I've written and now erased, the compact support property holds all the way up to gamma is equal to 1. And this is the part that was proved by Mueller and Perkins. And more than talking about any of my own ongoing work, I'm very excited to share this because I'm just engaged in a current flight of enthusiasm about it. It's not a very sophisticated thing that we do here, but we can rewrite this equation by just doing this. All I've done is factor out my 1/2 term, which I know gives me branching, and left out the noise and treated this here and left this outside. So I'm actually intended to give a quick explanation of why a square root coefficient on a noise term generates branching type behavior, but I forgot, and probably I don't have enough time. So if you'd like me to give you an intuitive description later of why square root times noise gives you branching behavior, I'd be happy to explain it afterwards. We know that this gives us branching, but if we just have some coefficient here, I mean, if this was a constant, it would just be like a constant multiplication. We'd be changing the branching rate. Now that's not quite the case because this isn't a constant. But what you get is a variable branching rate. And so what you get then is the interpretation of a solution to this equation with gamma, a general value of gamma, as a super Brownian motion, but no longer with completely independent branching rate, but the branching rate of individuals is just equal to some power of the local population density. And this to me was profound because generally, okay, we have our fixed values, gamma's a half, gamma's 1, we know how to interpret the equation, but somehow this gives you at least an intuitive picture of what's going on for any value of gamma via this branching interpretation. So we've got the branching, but then the branching is happening at a variable rate, which is, of course, dependent on the local state. Now, unfortunately, this means we can't use any superprocess techniques because as soon as you add a variable coefficient this way, everything nice, the branching property, all this nice independence goes out the window. So you have to still work hard to make this work for you. But this is what Ed and Mueller did in that paper for gamma less than 1. And what they did is construct the solution to this equation. They constructed an associated historical process. So I've talked a bit about what is, this is a kind of sketchy schematic of what a super Brownian motion is. And the state at time t is then you have a measure associated to all these endpoints of these different ancestral Brownian paths. So if you want to construct the historical process, this is this object in which we give a version of the process, but we keep track of all this ancestral information as time goes on. And if you want to understand the propagation or the support of the process is very useful because if we understand or are able to control these historical paths, then that can actually give us some control over the locations of all the path endpoints at time t. And so, yes, you make this quite technical object, the historical process, and they prove what's called a historical modulus of continuity. So we have our state at time t, consists of the endpoints, as a measure. But then we also have all this historical information about all the ancestral paths leading to those, which are a bunch of different Brownian paths, which will branch off from one another at various times. And the historical modulus of continuity gives a global Levy modulus for fluctuations of every single Brownian path in the historical process up to time t. And if you have this kind of historical modulus of continuity, that enables you to basically infer that the total kind of dispersion among all paths associated with the historical process is finite, and you get from that the support is compact. So I think that's quite neat. I haven't seen the technique used very much, but what's interesting is, so that this is something you can do now. If you have gamma equal to a half, you literally have a Brownian motion, super Brownian motion. You take gamma not equal to a half, now you've got some density dependent super Brownian motion, but you can make a historical representation. And if you want to go then and reintroduce a reaction term, well, this is going to be basically you think of it as, an FKPP type, for example, is going to be, xt minus xt squared. You could also make the historical, representation as a super process with interaction there and construct an associated historical process. Now, this method hasn't been explored much outside of this one paper, and it really depends what you're trying to do, whether this would be useful or not. But it does give you, another perspective and a rigorous particle perspective of the infinite particle limit for this kind of model. So I think that's a rather interesting perspective, which I wanted to share. Now, where are we at for time? Okay. So to finish then, I'll tell you, again, most of these results, I didn't put the exact years, but most of them are about the same age as me. And for everything I've talked about before, you assumed, I also said, this was a space-time white Gaussian noise. And what I've been looking at lately is, okay, I could have just called it W, but to make sure it's different, I'll call it L. And I've been interested in basically the same problem when we have stable noises. So, SPDE driven by non-Gaussian noises are, have received a fair lot less attention, but I think they're still quite interesting. And, so in addition, yeah, I'm an advocate for diversity in these different noise coefficients, but also for, a wide range of noises beyond just the standard Gaussian noises. So stable noises introduce, a host of new issues. In particular, they're of jump type. So solutions to the equation with Gaussian noise are going to be continuous, but the nature of the stable noise is that it's going to induce jumps in your density. So there'll be a set of times, countable but dense, at which the density doesn't exist because you're adding these atoms, but they quickly diffuse, or in the right parameter regimes, still have a meaningful notion of a solution. Let's just say L is a one-sided alpha stable noise. By one-sided, I mean that it only has positive jumps. Now, if I want to talk about non-negative solutions, that's kind of a requirement that I fix that, because if I'm allowing negative jumps in my noise, then, then that can actually just add a big negative atom, and then the solution won't actually remain positive. So we have a one-sided stable noise, and where these have been where these come up most often is, again, in the branching interpretation. So when we had the Gaussian noise, gamma equal to 1/2 gave us this super Brownian motion. We had a branching interpretation for the solutions to the equation. For the stable case, if L is an alpha stable noise, then if gamma is equal to 1/alpha, we get, again, the branching interpretation. And in particular, when gamma is equal to 1 divided by alpha, the solution to this equation is the density of a super Brownian motion with a stable branching mechanism instead of a binary branching mechanism. And so again, using superprocess techniques, we can prove quite easily that gamma equal to 1 divided by alpha, solutions to this have compact support. And so what I've been trying to do in some of my work is to basically prove the gamma less than 1 version of this theorem. So this is a work in progress, so I'll write it is tentative. The martingales lately have been behaving just how I want them to, so I'm feeling confident about it. And that's then that when gamma is less than 1, we've got this compact support property. And I will stop there. Thank you.
Thomas, any questions for Thomas?
So I didn't catch in your sort of heuristic argument about how we were going to extend this up to 1. You sort of talked about the historical process, but I didn't see where the 1, or I guess the 1/2 on the variable branching rate came in. Is there an easy way to see why that transition happens at gamma equals 1, or is that sort of more delicate?
I mean, it's a good question. I mean, basically the historical modulus of continuity that they prove goes up to 1, but I think it was already known at that point that for greater values of gamma, that the solutions were strictly positive. Another perspective entirely is the Lipschitzness of the coefficient. You hit the Lipschitz threshold at 1, which is big in uniqueness, but also going to be big for this kind of behavior. It's not a terrific answer.
So not so easy to see,
yeah,
but maybe.
There's the theory becomes so different, especially for gamma equal to 1, because it's a linear equation. So you can look at it as a heat equation with a random potential. And I'm sure there are a lot of arguments coming from this that can help you see that with gamma equal to 1, the support is full. And then beyond that, the heuristics suggest that if when you go past that, they should stay positive.
Amplify. Yeah, that makes sense. Thanks.
I could add that Mueller's original proof of this, of the strict positivity, was like kind of, it uses this comparison principle. It's quite technical. I think there are, there's connections with the linear multiplicative equation. This is connected to polymers and what have you. And I think there's some really neat proofs from more recent years that people have written about this.
So thanks. So you mentioned you restrict to one-sided alpha stable noise in order to have a non-negative solution function. But so if it is not one-sided, if the function has a positive and negative sign, anyway, you can ask about the compact support.
Yeah, that's right. I just haven't yet. But you can still ask about the compactness of the support. That's right. And I guess coming from like a branching and a population branching particle models background, I think typically about positive models, but that's right. And there is some theory for this for the Gaussian case as well, although I don't remember the results on hand. But thank you.
Okay,
yes.
Thanks.
If there are no further questions, why don't we thank Thomas and everybody else in this session as well.